sorry. What? Yeah, why isn't it showing it? I have to save the cross section, that's why. So when I exit, I believe. Let me check here. And let me insert now. Okay, so when I exit. Oh yeah, save. See, there it is, 750. Now I have to save the geometry data. Actually, I don't want to do that. I just want to. Go ahead. Okay. Now I have a new file, and there's the new cross section. Okay. That's all under cross section. There's one other thing I want to do. Go back to cross section. We'll come to ineffective flow areas, but you can also adjust the end values, put in levees and obstructions and other issues. So I think that's all I want to do there. All right. Now let's go to the next part. Close this. Edit steady flow data. So I'm just going to do one profile here with a flow change location. You see, I clicked on this at River Station 2000. At River Station 2000, I entered a flow of 6,000 CFS. Now, of course, as you go downstream, the discharge increases. And so I clicked on add a flow change, and I put in 500, and at station 500, and put in 7,000 CFS. Now, the most important thing here is reach boundary conditions. And here are the possibilities. You can start with a known water surface elevation, if you have a gauging station, critical depth, normal depth, rating curve. And here I've used normal depth, so I'm assuming uniform flow, and I entered a slope, which would correspond to a relatively uniform slope downstream reach. You may not always have that, but for this illustration, I've done that. And so what it does is use Manning's equation and calculates what the normal depth is at the downstream location. Now I'm doing a subcritical profile, so I'm only entering a downstream. See, if you're doing a subcritical profile, you don't enter anything for the upstream, only for the downstream. Okay. Okay, let's get wild and crazy. So let's put in an upstream profile. I don't know. And let's put in critical depth. And then okay. And apply data. Okay. Now, here's something I want you to do. If I'm in the right menu. And I'm not. Okay, let's do the next menu. Okay. Now this is all okay. So that's flow data. Now we go to the run, and you choose steady flow analysis. And here, let's just try mixed and see what happens. Mixed. And under options, this is what I want you to do. Go to, here's where you can change the friction slope method. You can put in flow distribution locations. So it'll use the ratio of conveyances. What I've done here is set some subsections, and so it will print out velocities across the subsections. But let's cancel that. Mixed flow, and you can change the calculation tolerances. Here I want you to note that, see what it's doing is selecting as the default the average conveyance. Remember we talked about this. And WizPro uses the geometric mean. So that's where you do that. So these are all options under steady flow analysis. Here's the one I want you to look at, critical depth. Check that box. Why is that? Because if you don't check that box, the program gets lazy and it won't calculate critical depth at every section. But to me, it's useful to have a critical depth calculated. I mean, this was written, I guess, in the old days when it mattered, when execution time mattered, and there's really no reason, but you should always compute critical depth. So just do that. I would do that for every run. I would always, under options, click under, so it's called critical depth, output option, and put a check mark there, always calculate. Other options, critical depth computation method. Yeah, so this goes back to the compound channel, multiple critical depths. The parabolic method is optimized. Okay, I think that's all I'm going to tell you about that. Okay, then you just hit compute. I may have messed it up, but no, it ran. So that's what you want. If you get that, then it ran. Close. Okay. Get this out of the way. Now let's look at view. Water surface profiles. Okay, so what's printed here is the dashed red line is the critical depth, so it's calculated in all cases. And up here, the blue line is the water surface, and the dashed line is the energy grade line. So the velocity heads are very small, and so the energy grade line is only slightly above the water surface. You can specify the profiles, the reaches, and so forth. Okay, so that's one particular view that's useful. Okay, and this plot gives you velocity in the channel, the right floodplain and the left floodplain. And so in the main channel, you can see we've got velocities of the order of 5 to 6 feet per second. And in the right floodplain, in both floodplains, they're of the order of 2 feet per second. So this is useful. And that's under general profile plot. also get tables. Let's go, here you can get a table for every cross section. And so all of the calculated data that you need is here. Let's start at the upstream end. So the energy grade line elevation, here's the total Q is 6,000 CFS, the velocity, that's the average velocity for the whole cross section. There's alpha, you see it's definitely not 1, it's 2.01. You can see how much friction loss and contraction and expansion loss there are from this cross section to the next one downstream, only 200ths of a foot. And then here are the values of various hydraulic variables in the left overbank, the main channel, and the right overbank. The top widths, here are the velocities I showed you graphically, hydraulic depths, conveyances, wetted perimeters, and the shear stress, which is important if you're considering a possibility of erosion. So these are cross-section tables, and you go through and get them for every cross-section just by scrolling through. See that? One to the next. Now, the other useful one is the profile summary table. And I like this one because you can see the actual computation of the water surface profile. So here you are at the upstream end, and here are the water surface elevations, the critical values. Let's blow this up. There's the critical water surface elevation, energy grade line slope. Notice that's the value that I put in right there. And there's how the velocities change through numbers and so on. Now there are standard tables. So you're looking at standard table 1, but standard table 2 has some other interesting data. It shows the discharges in the two floodplains in the main channel. And it also shows the friction losses. And you can see the biggest friction loss occurred from in the last reach, from 500 to station 500 to station 0.18 feet. And look how much the contraction and expansion losses are pretty small for this example. So those are the two standard tables, but you can then opt for creating your own tables. So for projects, these tables can actually be customized so that they become the output for a consulting report, which many consultants do. You just go directly from the hecras run to these tables. So, just kind of a brief overview. Do you have any questions? I think the questions won't come until you start using it. Then you're going to have lots of questions. Actually, this using it for water surface profiles is not so difficult. It's the bridge routines that become more difficult, and that's to come next time. Oh yeah. How about interpolations? Frankly, I always forget where this is.
It's under tools.
Okay. Yep. Cross-section interpolation. So between two cross sections, let's say. Okay, let's just do it between